So I'm Federico. I'm a MATLAB Student Ambassador of the University of Pisa. I hope now you can hear me. The seminar of today is an introduction on machine learning and in particular on unsupervised learning, which is a kind of branch of this macro topic of machine learning. And we will try to use this simple theoretical pills that I'll show you during the presentation to build something with MATLAB, understanding some basics function that we can use to address some problems. This seminar will be held in English. This is nice because hopefully this video will be available also for not just Italian people following our channel, but also for other people, others MATLAB Student Ambassador worldwide, which are interested in taking inspiration from our work here in Italy. And that's it. So I think we're almost there to start. As I said, this seminar is just an introduction. It will not be too much technical. It will be just enough to understand the topic for those who are not already familiar, and for those already, for those of you who already know these things, could be interesting just to understand how we can do these things in MATLAB. So I think I can skip to the presentation. Okay, so let's start. Okay, I would start my presentation showing you just for those who are not who don't know which resources are available for us from our university. So you should know that our university offers us a campus license, and the campus license gives us a lot of things. First of all, it gives us MATLAB and all its toolboxes. Second, it gives us the so-called self-paced courses, which are some online courses that you can find in your personal web page on mathworks.com. And they are very useful to learn things regarding also machine learning, but not only. There are a lot of courses on MATLAB, there are a few courses on Simulink, and you can learn a lot, trust me. And then for the University of Pisa, not only, there are also the MATLAB Student Ambassadors, like me, which should remind you all these things through posts and try to interact with you also with seminars, explaining you things and so on. So if you are, I hope no, but if you have never used MATLAB, this is the link for the University of Pisa to download the software and the toolboxes. And for those of you who came through this live event, not from the Facebook group, I would kindly ask you to join us on this Facebook group through the link, and also to join to our YouTube channel through the other link below. So this is the outline of the presentation and is exactly the same one that I show you in the Facebook group. So we will start by talking about what is machine learning. We will then just mention the importance of one of the self-paced courses that you can find in your online account, which is the MATLAB on-ramp course, the machine learning on-ramp course. We then give an introduction to unsupervised learning. And regarding this, we were going to talk today about dimensionality reduction and few algorithms that we can use to achieve dimensionality reduction, which are principal component analysis and multidimensional scaling. Then we're going to talk about cluster analysis, and in particular we will show these four algorithms: the k-means algorithm, the possibility to cluster data with Gaussian mixture models, hierarchical clustering, and also I will show you at the end one possibility to evaluate the cluster quality, so the efficiency, the accuracy of our cluster analysis. Okay. So let's start with what is machine learning. So I just take this picture from the net to show you that machine learning is a research field which is a kind of subset of AI, artificial intelligence. While artificial intelligence has just the aim to mimic human intelligence, machine learning is a way to do research in the field of artificial intelligence by building algorithms that learn something from the data. So in particular, we want to learn from experience. Here also from the picture you can see that a subset of machine learning, which is maybe more even famous than machine learning, is deep learning. And deep learning in particular is a set of machine learning techniques which typically employs neural networks to learn from experience just directly from data without, let's say, that one should add its knowledge to the variables that are employed in our data set. Okay, and this is maybe another interesting thing is that machine learning is able to learn things from data without relying on a predetermined mathematical model, which I think you can understand not always is possible, and most of the times is really difficult. So there are three main learning paradigms in machine learning. The first one is supervised learning, from which we want to learn relationships between an input and an output. Typically we have data, some input patterns called capital X, and we have also the labels for these data, which are the outcomes that we want to obtain through our prediction model. And supervised learning is aims to build a classifier, how it is called, or also a regressor, to predict the value of y based on our data. So it is called supervised because the part of supervision here is depends on the fact that we have labeled data. We have the ground truth, in a sense, of the data that we are trying to use. And our algorithm works in two phases: a training phase in which we tune the model, and an operating phase in which the model is fixed, and hopefully is, if it has generalized well, if it has learned a really functional dependency from X to Y, it will be able also to predict with new data. So another interesting paradigm is the unsupervised learning, which is, by the way, the topic of this seminar, from which, given a data matrix, a data set X, with no labels, so without any ground truth, we would like to find the underlying structure of the data and provide an internal representation of them. This can be done essentially in two ways, as we will see later. And so having no ground truth does not give us the possibility to have a reference to learn a model that describes data, but we just should rely on the internal representation of the data itself. Then another interesting paradigm is the reinforcement learning. Unfortunately, I decided to not talk with you about reinforcement learning just because I don't have the possibility in these days to build also a seminar on reinforcement learning, but it would be nice also to understand better this paradigm, and in particular, reinforcement learning is used mainly to control agents, in which we have an actor which is generating actions based on his system state. So he's doing some actions into an environment, and these actions are evaluated by another system that is called critic, which gives a kind of reinforcement signal that is a reward or a punishment for the actor in order to improve its performance. That's why it's typically used to control a system, because we have an agent who does not know what to do, and to improve its performance, we just build around this agent someone or something that gives him the idea if he is performing good or if he is performing bad. So this is the broad picture. This is the broad picture of machine learning. As you can see, you can find on the left branch the unsupervised learning, on the right branch you can find the supervised learning, and down below you can find the reinforcement learning. It's a broad field, as I told you, and today we decided to spend the rest of the seminar talking about unsupervised learning. Why machine learning matters before starting. So with the rise of big data, machine learning has become a key technique for solving problems, different problems in the following areas, for example, in computational finance for credit scoring, in image processing and computer vision for face recognition. This is in particular interesting when you deal with deep learning, which is the deeper side of machine learning, as I show you in the first picture. Then in computational biology, for instance, for tumor detection, drug discovery, DNA sequences, and energy production, automotive aerospace manufacturing for predictive maintenance, and also natural language processing, but there are many others. So you would ask me maybe, why machine learning with MATLAB? This may be more interesting because, as the previous part you can see from whatever website or whatever other video on YouTube, why machine learning with MATLAB could be maybe more difficult to find in the net, but I try to recap all the advantages in a couple of slides. So MATLAB makes the hard parts of machine learning with different things. First of all, you have applications for training and comparing models. That is, you have some tools and application that allows you to play with machine learning algorithm without really knowing what's inside, and in a really easy manner. Then you have advanced signal processing and feature extraction techniques, which are very useful for predictive models, to just run an algorithm that gives you features and extract the best subset of this feature for you, instead of just learning how to do it. Then there is also the possibility to have automatic hyperparameter tuning and feature selection. Okay, so this part of feature selection is something that I partially said when I talk about feature extraction. Then there is also the possibility to code to scale processing to big data. This is important because having scalable algorithm is not an easy task. If you maybe decide in another language to use the wrong API, you may encounter the problem that you have an algorithm that is not scalable, and when you give to this algorithm a big data set, this will run really slow. In MATLAB, you can find popular classification, regression, and clustering algorithms, and today we will talk in particular about some clustering algorithms and dimensionality reduction algorithms, and these are typically pretty good. So other things that may be interesting for you, which are maybe for a specific application, regards the coders of MATLAB. MATLABs have different coders, and we have coders for a coder for MATLAB, a coder for Simulink, we have an embedded coder and a GPU coder. All of these coders are useful in different cases, but just to wrap up the meaning of them, they allows you to generate fixed point C and C++ code that can be used if you just want to move from MATLAB to C, maybe because you are writing code for a safe critical application, for which C is typically more robust. But also we have an embedded and a GPU coder, which allows you to generate code not just in C or C++, but optimize to run on an embedded system or on a GPU target, which is really interesting, especially if we are dealing to real-time application or with deep learning algorithms in which we may need a GPU either for training and for the inference phase. So I just finished this part of introduction talking about the online self-paced course of machine learning on RAMP, which is for sure available for all of you. You can check these contents also on the official website of mathworks.com, and you can do this course. It takes like 2 hours and gives you a brief background of machine learning and how to deal with it using MATLAB. So in particular in this course you will see how to play with tables, which is a data structure of MATLAB, very useful to organize data, not just numerical data, but also data with different features like nominal attributes, ordinal attributes, and so on. And also it gives you the possibility to understand how to visualize data with MATLAB, playing with box plots, for instance, or with gscatter, which is a scatter plot function in which you can display data based on the class to which they belong. Then here you can also, in this course, you can also find how to train and evaluate a model, in particular a classification model, for instance, KNN, how to evaluate its loss, how to predict the output of the trained network, and so on. But we will talk about all these things from this seminar to the next one. And also it gives you the possibility to display the results of your machine learning algorithm, for instance using a confusion chart if you are dealing with a classification algorithm. So let's start. The contents that I will show you today are mainly taken from the machine learning with MATLAB course, also available for you online. This takes longer, but it's really dense and gives you a lot of knowledge about the field and how to play with MATLAB. In particular, we start from unsupervised learning. So I recap this broad picture for you. just to focus your attention, and we are now going to discuss to this branch. And in particular, let's start with this introduction. So unsupervised learning deals with the problem of looking for patterns in data without any supervision. So we have no labels, we have no ground truth. So this picture is funny and gives the idea that our algorithm, here represented as a robot, should understand how to group data without having no one telling him, telling it if it is true or if it is correct or it is wrong, the way in which it organizes all the data set. So there are two main approaches adopted in unsupervised learning, which are dimensionality reduction, used to find subspaces where data are well organized, or cluster analysis, also called clustering, which is used to group data with shared attributes typically. So there are many issues with unsupervised learning. Unsupervised learning is typically harder than supervised learning tasks. So it is also difficult to understand how meaningful is the work that you did with an unsupervised learning algorithm. Because since you don't have labels, it is not so easy to understand if you have drawn meaningful results or just grouped data in some sense. Typically, unsupervised learning algorithms may require the definition of an objective function. This is especially true for clustering. If you want to find an internal structure of the dataset, you require the algorithm to proceed with a heuristic approach and not to check all the possibilities, all the combinations, because it is not feasible for an algorithm. So despite these issues, why we want to use unsupervised learning? So we want to use it because for many supervised learning algorithm, we require a lot of data, and having a lot of data require annotating a lot of labels, and we may not be able to to label all this data. So one way to deal with automatic labeling is to use unsupervised learning techniques. Also, there may be cases in which we don't know, of course, classes and the ground truth, and we want to understand how to divide data. In this case, for example, in data mining problem, we required unsupervised learning to, in some sense, not automatically label data, but try to give a label to data to further processing. And also, unsupervised learning is very useful also in supervised learning problems to gain an insight on the structure of the data before designing a classifier, a regressor, and so on. So it is a very useful technique also as a pre-processing tool. So from now on, we will refer to our data as a kind of matrix or a table in which along the rows we have the observation, which are capital N observation, meaning that the size of our data set is N. And along the columns, we have the features or attributes or variables of our data. This is just a representation. You can also flip this matrix, but it is useful to understand the small part of mathematical background that you can encounter in further slides. That's it. And in particular, the unsupervised learning approach is requires to understand how we can compare these data, so these different observations, how we can compare them. This requires the introduction of a concept of similarity, which is used to assess how alike or unalike objects are in comparison to one another. Similarity, and this similarity just tries to capture this property, and in particular, as you can imagine, a similarity measure of two objects will typically return a small value, in particular 0, if the objects are unalike, so they are different to each other. And the higher is its value, the higher the value of the similarity, the higher the similarity between these two objects. They are more alike. More alike. And on the other hand, a dissimilarity measure works in the opposite way, so it returns a value of 0 if the objects are the same, actually. So if you are comparing two identical objects, and it will gives you a high dissimilarity value if the two objects are alike. So there are many ways to measure proximity and similarity of the data. In particular, this requires to know which kind of attributes describe your data. In fact, depending on the kinds of attributes that you have, you will need a different way to measure the proximity of the data. If you have two numbers, you may just require to do a subtraction. If you have two vectors, you require a norm metric. If you have an array in which you have nominal attributes, you have to understand if there's a rank between them, so if they are ordinal in some sense, or if they just mean different things. So if you have a nominal attributes, which is the color of, I don't know, a flower, the same distance that there is from red to yellow would be the same that there is from red to blue. I mean, there's no encoding, as it is said, in just the color, or at least, I mean, you can also try to encode this information, but you would need to treat this feature in a different way. So examples of metrics that you can use to deal with machine learning, unsupervised learning problems are the Jacquard coefficient. If, for instance, you have asymmetric binary attributes with just takes value 0 and 1, no values in between. Euclidean distance for numeric attributes, in particular, I would say Minkowski distance, which is the generalization of the p-norm. So you can generalize the concept of distance and norm to any dimension. And also cosine similarity if we deal with sparse numeric data. So if we have high dimensions, if the number of columns of our data is too long, the risk is that similarity matrix becomes inefficient to describe the distance, the proximity from two data objects. This is also called the course of dimensionality problem, and there are ways to deal with this, and in particular one way is to choose a better metric to deal with it, for instance the cosine similarity. So it is important to define or select similarity measure. That's why I placed this slide here, because results can vary depending on the similarity measure that we use. As I said before, if we have high dimensionality, the choice of an Euclidean distance may not give us the results that we expect. Instead, using a cosine similarity may help us to find a better representation of the data. we are now going to switch talking about dimensionality reduction. And so, if you remember our big picture, we're going to talk about this branch here, where you can see some names like meaningful compression, big data visualization, structure discovery, and so on. So they are all applications or subfield of dimensionality reduction that can be interesting. So I decided to introduce you this problem of dimensionality reduction, recapping for those of you who played with PlayStation and Game Boy, the image of Mario driving in a 3D race kart, racetrack. And so if you think for simplicity that this road is large exactly as your kart, so imagine that you're running in a street that is whose width is exactly equal to the dimension of your car. If there's a kind of hole below of your cart, what would you see? What would you see if you don't look at the street, but you look through the hole that is placed at the bottom of your cart? So you'll probably see something like this. You will see just a rainbow, a string containing all the colors of the rainbow, because if you think that you have a small hole from which you can see all the road at the bottom of your cart, you still see the same image even though you're running on a 3D path. This is really interesting because this simple example is what is behind also the concept of parameterization in analysis and in differential geometry. So the fact that from a certain reference point of view, we can see a 3D geometrical shape as just 1D geometrical shape. So this is interesting for me. So dimensionality reduction is the problem of finding the dimensions along which the dataset shows the greatest variability, which correspond to the most relevant parameters of the dataset. So, as I said, it belongs to the unsupervised learning paradigm, according which we are trying to find the inner structure of our data. In particular, I would like to point out that dimensionality reduction is not exactly feature selection. So they are different things. In fact, even though both methods seek to reduce the number of attributes in the dataset, feature selection is just the process of selecting a subset of this feature and the other ones are discarded, while dimensionality reduction combines all the features that we have extracted from our dataset and we try to combine them. Then we reduce this combination. So it's not exactly the same thing. Feature selection just takes some of them. Dimensionality reduction takes some of them but combined together, which is more powerful sometimes. So the first approach that I want to show you to deal with dimensionality reduction is the principal component analysis. The principal component analysis is a simple statistical method which aims to find the directions of the dataset in which we have a higher amount of explained variance. This can be achieved with a linear transformation using PCA with just a rotation. So we have a matrix Q which rotates our dataset X in order to achieve a different representation in which the projection of our dataset in the new reference frame has a meaningful meaning, is more meaningful. So taking a look at these pictures, you can see that if we think about a b-dimensional data set, and x1, x2 are the 2 dimensions of our data set, this rotation just produce 2 new axes, which are P1 and P2, called principal components, from which, if we project our original data to these new axes, we can get, for instance, the result that we have below. So projecting the red dots along P1 gives exactly the blue dots as I have drawn. And this gives us the possibility, if we neglect part of this axis, as we did below, just taking in consideration P1, to reduce the dimensionality of the problem, considering 1 axis, for instance, instead of 2. So this is a more detailed slide which explains you how this rotation can be obtained. This deals with the concept of eigen decomposition of a matrix, or singular value decomposition of a matrix, and in particular what PCA aims to do is to find a rotation whose outcome is to obtain a diagonal matrix, essentially. And this diagonal matrix, which is A transpose in this slide, is just the combination of 2 matrices which corresponds to the projection of our data in the new axis. So essentially, what PCA tries to do is to find a matrix which rotate our dataset and rotate this dataset such that its covariance matrix or its correlation matrix becomes diagonal. In this way, we are pretty sure that there is no correlation between the new axis that we have found in the new reference frame, and so highlighting also the main orthogonal directions of variability of the dataset. And I would say again orthogonal. However, not all the principal components need to be kept. So we don't want to just rotate our dataset. Since we want to achieve a lower dimension problem, we just need to reduce these components that we want to keep. So after our rotation, to achieve a data compression, we have to just keep only parts of this axis where we are projecting our dataset, just a part of these principal components, and this will allow us to effectively achieve a dimensionality reduction. So you can do this in MATLAB by using the PCA function, and in particular, if you keep just the first, the second, and the fifth outcome of this function, you would retrieve the matrix, what I called before, all the P columns, the P axis in which we want to project our dataset, which is the matrix of principal components, the matrix of the scores, which is the matrix containing our data projected in this new axis, so in the PC's axis. And then another interesting features that we can derive from the PCA algorithm is the percentage of variance explained by each component. So we can understand the meaning of the amount of variance explained through our projection by analyzing the pexp variable, which typically gives you in descending order all the amount of variance explained by each of the principal components. And then for sure also the data, and this corresponds to the X matrix that we discussed at the beginning of this part. So if you suppose that your input matrix has two columns which contain the values of the observed variables x1 and x2, so we have endpoints, but we have just two features, two observational variables, two attributes that are depicted in this Cartesian plot. So performing the PCA can give us the following information. From the matrix P, we have the matrix of the eigenvectors, which are the columns of the matrix that gives the rotation, also called the principal components, the ones that we want to rotate, where we want to rotate our data set. And we have also the amount of variance explained for each of these principal components. So if we consider what is the meaning of the first column of the matrix P, we would discover that this is can be used to draw the equation of this line, that is the first axis in which we have projected our data. And on the other hand, if we also use the other second column of our matrix P, we would end up in deriving the second principal component of our data set, that is the second axis where we want to project our data set. And below you see also the amount of variance explained using just one component, so just representing data with the P1 axis, or representing the data just using the P2 axis. And it is very easy to understand why P1 keeps the highest amount of variance. So this is to show you that if you reduce, if you want to see the projection of in just one dimension, you just need to evaluate or display the value of the scores matrix, which is the matrix again in which you find the projection of your data in the principal component axis, in the principal components. So an interesting example where you can use PCA, for instance, is to have a dimensionality reduction of images. So here I took 40 maybe images from this website, which is a website from which we can take images generated by AI algorithms. And I decided to apply PCA in order to have a 2D visualization of these images, which is pretty strange if you think that images has a really huge number of dimensions, because they scale with the square of the number of pixels. So the first thing that you have to do if you want to reduce a dataset like this is to flatten your data. So imagine that you have n images and each of the images has n pixels. The way to organize your dataset according to how we discussed at the beginning of the seminar is to build this kind of matrix in which along the rows we have the data for each image, each of which is a vector, just a vector, that results in the flattening of each image. That means we take all the pixels of our image and we reshape these pixels in order to achieve a one-dimensional a vector of n squared pixels along one dimension and just one along the other dimension. Then once we achieve this kind of data set, we can apply PCA as before. So this is the result if you do with the dataset that I used. Then I will show you the code to do this, but for those of you that are not online now, you will find in the description of the video a link which brings you to the material and to this script. And as you can see, this could be an interesting way already to group data, to reduce the dimension, because you can see that most of the women are placed on the left of this Cartesian plot, and most of the men, almost all the men, are placed on the right side of the Cartesian plot. And personally, I can also distinguish a little cluster of elderly people on the right upper side, but I mean, maybe I am biased because I did this. And by the way, this is just, we compressed the dimensionality of the problem in just 2 Cartesian axes. However, PCA is not able to capture well data components if we have nonlinear problems, highly nonlinear problems. For instance, if we want to map nonlinear manifolds, which is the example of our 3D race kart of Mario before, okay, where Mario was running before. So in that cases, you need other techniques to do dimensionality reduction. Here are some examples. You can use, for instance, isomap, summon mapping, multidimensional scaling, which is the next topic that we are going to discuss about, and also t-stochastic neighborhood with embeddings. I see a question now. So, come si comporta la PCA con dataset non bilanciati? So, this is an interesting question. PCA with unbalanced dataset, first of all, tends to reason with the lower of the dimension between the number of observations and the number of dimensions that you have for each data. I try to explain this better. I go back here. So in this case, we have n images, which in my case is smaller than the number of pixels that we have for each image. In particular, it is also smaller than the square of this number of pixels. So PCA in this case does not treat the dimensions, the number of dimensions of the independent dimensions as the number of squared pixels, but as the number of images. So in this case, it is as if we were dealing with I don't know, n images dimensional problems and not as an n square pixels dimensional problem. So this is the first thing to clear. And another important thing is that PCA, of course, is biased towards how our dataset is constructed. This is also true for clustering algorithms, because when we deal with this algorithm, we're just looking at the inner structure of the data. And so if we are not able to provide a data set which is sufficiently rich for our algorithm, we will end up in a suboptimal result. In my cases, you may you may understand that also the possibility, the reason behind this clear distinction between women and men in this Cartesian plane is due to the fact that the number of pictures of women was 1/4, okay, with respect to the pictures of the man. So autonomously, the amount of variance that we are deriving, the direction of the variance is biased towards the fact that the features of the man are more present in the data set with respect to the features of a woman. So this was really a good question. So PCA depends on how the data set is structured, and so on how it is balanced. You can deal with this problem also if you want to deal with this when you have clustering algorithms in the same way you would deal with this for classification. So you have the possibility to split the data set to have to balance it, and then use the remaining parts, the remaining data, and see what is the result for the PCA, for the linear combination that you extract for the remaining data. So we're now going to talk about briefly just distance. We said at the beginning that an important thing to when talking about unsupervised learning, but in reality also supervised learning, is to understand how to compare data. To compare data, we need a similarity metric, or a similarity metric. Similarity brings up to the concept of distance, and the concept of distance does not necessarily implies the properties that you see in this slide. So this is a particular case of distance, which is also called, from the mathematical perspective, a metric, in which we have these further properties satisfied. But in general, it is not true for every similarity and dissimilarity metric. This is true for those who are recognized as distance metric. Why this is important? This is important for a consideration that we will talk about in the next slides. So again, if you think that capital X is our matrix containing all our data, so along the rows we have n data object, along the columns we have the number of dimensions or features. Using multidimensional scaling, which is the second technique that I want to show you, gives us the possibility to again reduce the dimensionality of the data set by finding just a smaller number of features in which we can try to preserve the distance between data objects. So as you can understand from these words with respect to the case of PCA, we are not interested in anymore in just find axes in which the projections are minimized. This kind of reasoning method, the reasoning method of PCA, is regards in a probabilistic fashion and aims to build an orthogonal set of feature. Instead, here we are just not talking about orthogonality. We are just playing with measures of distance, and we want to find a smaller set of features in which the distance is almost preserved between data points. So this is just a slide more formal to make you understand that with classical multidimensional scaling technique, we want to find a matrix XP, which this time has the number of variables describing each data object is P and no more M, where P is smaller than M, and so that the distance between objects still remains the same that we would have using our original data. In particular, this problem has not a unique solution because you can understand that when you deal with distance, you can place your the origin of your reference frames wherever you want, and this of course gives an infinite amount of solution for this algorithm, and in particular you should impose a further constraint to deal with this problem, for instance imposing that the sum of all the data points is equal to 0. So this is again a part of theory that is behind the multidimensional scaling. Essentially, multidimensional scaling starts from a matrix that here is called D square, which is the distance matrix of our dataset, and in particular in each row we have the each entry is the distance between the eth feature of one data point with the jth feature of the other one. So essentially, instead of working on the covariance matrix or the correlation matrix of our dataset, we are building a distance matrix here, in particular a distance square matrix, from which we can try to build a subset of variables useful to describe our dataset. Here in particular, I would like to highlight that this operation of double centering, which is an operation that is performed by the multidimensional scaling algorithm to achieve a similar matrix with respect to the case that we use to work with PCA, but in this case this matrix is similar just because we are dealing with a Euclidean metric. If you would instead use just another metric, the result would be different, but this is explained better in another slide. So again, multidimensional scaling works with eigen decomposition. This is roughly how the algorithms work. So you compute the matrix of square distances, while in the other case, using PCA, you would compute the covariance matrix or the correlation matrix of the dataset. Then you do the double centering, which is used to achieve a unique solution instead of multiple solution that arises from the fact that you could fix the reference frames in every point in space. Then you do an eigen decomposition, and from this eigen decomposition, you can extract a matrix whose eigenvectors are the new basis for your dataset, exactly as in the case of PCA. But again, I recall you that there's a subtle difference between these two methods. In particular, PCA minimize dimensions, preserving covariance. So you are trying to rotate your dataset such that the covariance between different features becomes 0. Instead, when you use multidimensional scaling, you're trying to preserve distance. This is very similar, and in fact, in the case you're using Euclidean distance, these two approaches are the same, but if your distance matrix from which you start is not computed with Euclidean distance, this would end up with a different result. And of course, this result depends on the metric that you used. So with MATLAB, use multidimensional scaling is possible before computing the distance matrix, as I said, using the pdist function. The pdist function takes as input our data matrix, and you should also give as a further parameter the kind of distance matrix that you want. It may be Euclidean, it could be a Manhattan distance, which is another kind of distance. You could use a cosine similarity, which is the one that I explained to you for sparse dataset. You can do whatever you want. And this will build up a matrix D containing all the pairwise distance of your data object. So D, as I said, is the distance or dissimilarity. Okay, here is called dissimilarity vector because, as I said, distance and dissimilarity have approximately the same meaning. Then you have the matrix of your data, and then, as I said, you have this optional parameter to specify the method to calculate distance, which is by default Euclidean. Then, to run multidimensional scaling algorithm, you should take the result of the pdist function. So you have to plug your matrix of pairwise distances to CMD scale function, and the CMD scale function will return to you a matrix X, which corresponds to your new dataset with the new variables that you have found. So it is not as in the case of PCA that you receive back the principal components. So you receive back the axis and you receive back the projection of the data in the new axis. Here you just receive back the projection of the data in the new axis and eventually the eigenvalues of the matrix X transpose, which is a kind of correlation matrix of your data set. So you can use, as I said, the eigenvalues E to determine, before was the amount of variance, here is to understand how informative is that specific dimension. And by cropping the columns of X, you can provide a reasonable representation of the dataset with a fewer amount of dimensions. So if the first P eigenvalues are significantly larger than the rest, so the first P values of E are significantly larger than the rest, you can just take the first P columns of X, which are enough descriptive for your dataset. So here is another example with images. This is from the MNIST dataset, which is a famous benchmark for trying algorithms. If we do as before, so we flatten all the images that we have in our dataset, we are able to retrieve three-dimensional representation of these images using multidimensional scaling. So as what we have to do, as I described before, is to compute the pairwise distance between each of the images that we have in the dataset. Of course, after we have achieved a flattened, a reshaped representation of these images, so we just have to obtain vectors instead of matrices, and then we can use all these vectors in a unique matrix to compute first the distance matrix, and then from this distance matrix we can use multidimensional scaling. And by retaining just the three components, this is the kind of visualization of the dataset that you have. As you can see, each color corresponds to a different digits of this dataset and a different image of the dataset, and in particular the color is representing of the labels. And you can distinguish pretty well the ones from the two from the zeros. So it is a quite good three-dimensional representation of this dataset. Again, if you use the Euclidean distance, you would find the same result using PCA. In this case, I use cosine similarity, and I found personally a better representation of the ones that I found using the Euclidean one. So that's why I plugged this image here. Again, I have a script that does this, and I will show you later this, or if I have not enough time, I will give you, I will share with you the link of the material from which you can take this, the live script that does the job, and you can play with it. We're now going to talk about clustering algorithms, which is, if you remember, starting from our big picture, this smaller branch here in unsupervised learning. So, given a set of points belonging to some space, here is more formal the definition, so I also written with a notion of distance between points. Clustering aims at grouping the points into a number of subsets called clusters, such that some desirable features of these clusters should be respected. The first regards the compactness. So points in the same cluster, we want that points in the same cluster are close to one another, and this is the notion of compactness. Then we would like that points in different clusters are distant from other points belonging to other clusters, and this is the notion of separateness. So we want that, of course, if data points allows this to us, that the recognized clusters are recognized distance to each other, meaning that there is a certain there are different properties from a group that we recognize to another group that we recognize. Again, as I said many times in this presentation, distance captures a notion of similarity. So points that are similar are closer to each other, and points which are distant are dissimilar and far to each other. A clustering problem is usually defined by requiring to optimize an objective function. Not every time you recognize which is the objective, even though the behavior of the algorithm is very easy to describe, but each of these each clustering algorithms, most of the clustering algorithms require to minimize an objective, which means to proceed in an optimization manner instead of just greedy checking every combination among data points. Clustering or cluster analysis is a fundamental task in data analysis, and it is used in many applications like image processing, information retrieval for telecommunications, biology, and so on. And it is often a useful preprocessing step in other analysis tasks. In fact, clustering can be used to summarize, compress data, but also to detect outliers, which is also an interesting problem for in machine learning applications, which can worsen the accuracy of your model. So this is a table showing you the kinds of methods that are available for clustering algorithms. I take this from a book. I'm pretty sure this is not exhaustive at all, but if you maybe understand that some clustering algorithms may combine different of these methods, maybe you can collect all the kinds of clustering algorithms that you can find everywhere. So they are essentially divided in partitioning methods, in hierarchical methods, in density-based methods, and in grid-based methods. So the idea behind each of these methods is the kind of objective that we defined. In some way, we want to find an objective which gives the best partition. In some way, we want to give an objective that evaluate a certain quality of the cluster closeness and separateness, maybe because of its density or maybe because of its distance. So I mean, there are many things to say about this kind of classification. What I can tell you is that today we're going to discuss essentially examples of partitioning methods and hierarchical methods. So the most famous, probably the most famous partitioning methods is the k-means clustering algorithm. The k-means clustering algorithms starts what are called cluster centroids in random positions of the space of your data, and then all the data are assigned to the clusters based on the distance from that specific point to all of the cluster centers. So if you watch the first images, the red points here, I hope you can see the cursor, the red points here is compared with the distance of all the centroids, and if it is closer to the centroid of the red cluster, it will be automatically assigned to the red clusters. So this is an iterative procedure, so you will keep doing like this until the algorithm converges. And here's the nice thing, that the algorithms always converges, so you just have to wait until all the points are assigned and remain assigned to a unique cluster. So in the second image, you can see, for instance, that the two green dots are closer to the new blue centroids, and for sorry, the contrary. So that points were closer to the green centroid with respect to the blue one, and then they change assignment from the first to the second picture. So the idea is the following: you start with a random selection of centroid in space. You assign points to the closest centroid, and then you update the centroid of the cluster. How you update the centroid of the cluster? You update it by a simple averaging your data point belonging to that cluster, and by just averaging data, this corresponds to moving the centroid in another location in space, similarly to how you would compute the center of mass, for instance, of a physical system. Okay, and after computing the centroid, updating the centroid, you then update the belonging of each of the points to the clusters. So when you move the centroids, typically what happens is that also the distance from data points and the new centroids is different, and when the distance changes, you may end up in a different assignment of the points with the current cluster structure. In the last picture, you also see a way to visualize this with the Voronoi tessellation, which is a 2D representation of the what could be improperly called the decision boundary of this clustering technique. So essentially, they give you a representation for each point in space, how that points would be, to which cluster they would be assigned. In MATLAB, you can use the k-means, you can run k-means algorithm using the k-means function. In particular, the inputs taken by the k-means function are, again, the data matrix with the convention that I told you, and the number of clusters. And the result is a vector whose entries are is an integer index which represents the cluster to which that specific point at that row belongs to. So two important observations here for the k-means algorithm are the fact that it requires a number of clusters, so you should know the number of clusters that you want, or you should try to evaluate different numbers of clusters to achieve a good result. And also it works with numeric matrices. So in case you would need to work with hybrid data in which you don't have just numerical features, but you also have nominal features, ordinal features, binary features, and so on, k-means is not the algorithm for you unless you encode this feature with a number, and this is also a possibility that can be done. I didn't mention here in the presentation, but there are some functions like dummy_var which helps you to brings categorical data, nominal data to a numerical representation, and it's not the only way to do this. Otherwise, you should use a different kind of partitioning method. So there are further options that you can specify for k-means, which are the distance metric, which could be correlation, which could be Euclidean. There are many. You could specify the starting location of the cluster centroids, because as you can imagine, the position of the starting location of the algorithms has a weight in the outcomes of the algorithm. In fact, what typically this MATLAB function does is to run many replicates, which by default I think they are 5 or 10, in order to derive an average result for the cluster, for the groups of data. So the cluster that you would visualize running the k-means functions is the result of a kind of majority voting among many replicates, due to the fact that the starting location of the clusters has an influence on the result itself. And also you can specify this number of replicates, adding the option start and saying what is the number of replicates that you want. Of course, if you just place start 1, you would probably end up with different results at each run of the algorithm. Another clustering algorithm, which is a kind of partitioning method, but not exactly, because according to the table that I showed you, a partitioning method requires that each data point belongs to just one cluster, but here is not the case. This kind of way to do clustering using Gaussian mixture models works similarly, but using Gaussian distributions. So instead of starting centroids of the cluster, here you start the mean of k Gaussian distributions, then you evaluate the belongings of each of the data points to the two distribution in a similar fashion as you would evaluate the belongings to a point to a centroid to a certain cluster. So you don't compute exactly distance, you evaluate probabilities here, and then by evaluating the belongings of each point, you can update the statistical parameters of your distributions. So as you can see in the picture B here, after we evaluated the belongings, moving to picture C, the two Gaussian distributions are updated based on the values of the mean vector and the covariance matrix, which are, by the way, the only parameters needed to specify the distribution, the Gaussian distribution in space. And this, again, is an iterative procedure. This kind of algorithm is called expectation maximization, and this, unfortunately, does not necessarily converge, but when it converges, will give you some Gaussian distributions with almost which should fit your data. This also gives us the possibility to distinguish between soft clustering and hard clustering. So when we think about hard clustering, is a kind of clustering in which each data point can belong to just one cluster, and it is not the way in which our Gaussian mixture model works. This is the way in which a partitioning method like k-means works. And if you try to do this with a dataset like this, as I done in the demo that I'm going to provide you, you can see that the green clusters that you see below in the figure is not properly correct. So when you have overlapping clusters, hard clustering technique, a fully partitioning method, is not what you want to cluster your dataset. Then there are some soft clustering techniques in which you can assign points with a certain probability to a cluster or to another, but you don't just keep that assignment. You still maintain the possibility that this point, or the probability that this point, can belong to all the other clusters. And this is very useful. In fact, from the same dataset, if you run a Gaussian mixture model that is a kind of soft clustering algorithm, this is the result. you would end up with. So don't forget this distinction, because some problems can be very difficult to solve with hard clustering techniques, and some other are and the same problem may be very easy to solve with a soft clustering technique. Of course, there is the vice versa can hold, but this was just a slide to provide you with this concept. If you want to fit a Gaussian mixture model in MATLAB, so you want to cluster data according to Gaussian distributions, you have to use the fitgm_dist function. And after having called the fitgm_dist function, you need also to call the cluster function. Why you need to call two functions? You need to call two functions because the fitgm_dist function builds the number of clusters that you obtain and some properties of these clusters from the data and the kind of and the number of distributions that you want to specify. Instead, by using cluster, if you pass the mixture model that you obtain after calling the fitgm distribution, you are able to assign to each kind of point in your data set the corresponding cluster to which this data belongs, and also the probability with which this data belongs to that cluster. So, I mean, the information that you see from the variable idx that you see in this slide is exactly the maximum of the probabilities that you see in the P matrix that you obtain by the same function. So, wrapping up, fitgm distribution is a function that builds a mixture model with k distribution, which k is a parameter to specify, x is the data matrix to specify, organized in the same way we discussed before, and cluster is a function, a further function that you need to use to call the GM model, the mixture model that you build together with your data. And this assigns each data to the corresponding clusters that you built according to the GM distribution that you found. But this is not the only information that gives you the function cluster. The same function gives you also a vector, or better a matrix, but a vector for each data point of probabilities that of course sum up to 1, each of which represent the probability that that specific point belongs to one of the clusters. We're going to start now talking about hierarchical methods. So the best way to start talking about hierarchical methods is probably with an example. Hierarchical methods, differently from partitioning methods, requires not only or better, they do not require just a notion of distance between data points, but they also require a notion of distance between clusters. So if this is our data set, having knowledge of distance between clusters means to evaluate which would be the distance if A and B belongs to the same cluster with respect to, or better, rephrase them keeping the example. So a hierarchical methods works in an agglomerative, which is a bottom-up approach, or or a divisive approach, which is a top-down approach. The main difference between the two approaches is that with an agglomerative approach, you start with each of your data points belonging to a unique single cluster. So at the first iteration, you would have, in this case, 9 different clusters. And then at every iteration, you join points, creating other clusters once at a time. So you evaluate the distance between, in the first iteration is just between points, but then as you move on, since each point belongs to clusters, you should evaluate the distance between clusters, and according to a certain metric, you join these clusters one to another. Conversely, if you have a divisive approach, you would done in the opposite way, so you would start with all the points belonging to the same cluster, and at each iteration you would divide this cluster in different subclusters, and so on and so forth, depending on the metric that you define for the distance between the points and the clusters. So here we started with, here I put an example with an agglomerative approach, which is probably the simplest one. And you can see that after 4 iterations, since A is closer to B with respect to J and all the other points, J is closer to H, C is closer to D, G is closer to F. After 4 iterations, we would have the 4 clusters that you see with the color code in the slides. And this corresponds with a graphical representation, this joining with a kind of diagram like this, that is a tree structure diagram called dendrogram. The dendrogram is built together with, can be built together with the advancement of the algorithm, and gives us the idea of how during the iterations the algorithm is joining the different clusters, the different data points, until we reach a unique cluster. So after 6 iterations, since E is closer to C and D, or maybe G and F, but here is not a problem since we speed up to of 2 iterations. Since E is closer to C and D, and also the cluster of CDE is closer to the cluster of GF with respect to the cluster of J, H, and A and B, after 2 more iterations, the points C, D, E, G, and F are joined in a unique cluster. And this is represented with the dendrogram in the figure, in which, as you can see, the points C, D, E, F, and G converge to a unique branch in the end. And finally, if you keep going, this would be, of course, the result. You keep merging clusters based on a distance metric until you achieve a unique cluster. And when you achieve a unique cluster, you arrive at the root of this dendrogram flowchart. So I add this slide to remark the fact that during my explanation I used 2 different terms for distances. I used the term distances between data points, which is the conventional distances that we use to measure similarity and dissimilarities between data points. But this is not the unique distance metric that you need when you use a hierarchical method. In fact, you also need to establish how to measure the distance between clusters, since when you want to merge different clusters that are already formed with more than 1 point, you need a definition of a distance between them. And the algorithm proceed in an iterative way by comparing the distance of all the clusters to each other, and merging them depending on a certain criterion. These are examples of distance metrics for the distance between clusters, and in the example that I showed you in the previous slide, I used in particular a single linkage metric, how it is called in the literature, and again I want to remark the fact that in computing the distance between clusters, of course, appears the distance between data points, but they are two different things. In fact, here, as you can see, the distance between the distance between two clusters, Ci and Cj, is evaluated by performing the minimum among the possible distances of a data point P and a data point P prime belonging to the two different clusters that we want to evaluate. But there are many, and in the same way as the distance metric that you select for points can affect the outcome of the evaluation of the similarity between the points, also the selection of one of these linkage metric can affect significantly the result of your hierarchical clustering algorithm, achieving also a different dendrogram representation. So in the following slide, what you see is exactly this. We have the same data set. We are joining clusters to each other based on different linkage metrics, different distances between clusters. And if we use a single linkage, we would achieve exactly the dendrogram that we found in our example of before. Instead, if we use a complete linkage, which is okay, if we move back, is a way, is the maximum between the distance of the 2 points instead of the minimum, where the 2 points belong, of course, to different clusters. Complete linkage, as you can see, tends to group overall data instead of instead of building a bigger cluster on one side and then joining the other points one at a time. So complete linkage, in a sense, evaluates from just the first iterations also smaller groups of data, and you can do this in MATLAB by first building the linkage, which is Z here, with the variable Z, and this linkage is linkage function takes as input the data matrix X, takes as input also a linkage metric. Here, for example, I select single, and also a metric to measure the distance or similarity between data points. So you require, again, two different distances. You can visualize the dendrogram built from this linkage using the dendrogram function and passing the result of the linkage function, and then to obtaining real clusters in the end. After you build your dendrogram structure, you just need to specify a criterion from which you can select the clusters. So differently from a partitioning method, a hierarchical method builds the whole story of the whole history of your algorithm, and from the whole history of your algorithm you can decide from the dendrogram itself how you would like to divide your data points, how you want to cluster them based on how they are joined together. You may decide to select a maximum number of clusters, as I expressed here with the function cluster. So if you select a max cluster equals to 3, you would end up with 3 clusters. So automatically the function organized the data points in the 3 clusters according to the dendrogram that you have. Otherwise, you could also select a threshold, and by selecting a threshold, you would find at the output all the clusters that you have for that specific value of the threshold. Again, this is the explanation of what I said before. You have to build first your hierarchical structure, which results in the visualization of the dendrogram by calling the function linkage, from which you pass your data matrix. You pass linkage matrix. Here is the word method in this case. And also you have to pass a similarity matrix to measure the distance between points. Here, the cosine similarity. We are now at another interesting topic in cluster analysis, which is how I evaluated the cluster quality. So if you think about this, when we deal with supervised learning, we have a ground truth, we have labels, and we can assess the accuracy of our model based on techniques such as based on metrics such as accuracy, such as other that we will see in the next seminar, like precision, recall, and so on, because we know what is the outcome that we need for our machine learning algorithm. In the case of cluster analysis, we don't have such information. We don't have it for any unsupervised learning method. So we need a kind of way, a kind of criterion to give us a feedback of what we are doing. So as I said, when the ground truth of a dataset is not available, we don't have labels, and we can evaluate the cluster quality based, for instance, of the separation of clusters and also compactness of the clusters. These are also the 2 features that I placed at the beginning of the introduction on cluster analysis, because they are typically the 2 features that you may want to address when selecting one clustering algorithms with respect to another. But they are not necessarily the best feature that you have to find for a better clustering. And in the demo that I'm providing you, you would see that the method that I'm going to explain you to evaluate cluster quality is not as efficient as we expect to understand really if we obtained a real cluster separation, a real grouping of our data set. So the kind of metric method that I'm going to explain you to evaluate cluster quality in this seminar is the silhouette coefficient. The silhouette coefficient can measure the clustering quality based exactly on these two features, separation of clusters and compactness of clusters, which again is a way and not necessarily is the best way to measure cluster quality. So to evaluate cluster quality based on the silhouette coefficient, you have to compute this value for each data point, and this value is S of O. S of O is computed based on two auxiliary parameters, which are B and A, where A is the compactness of your clusters, and B is the separateness of your clusters. So the compactness, as you can see, can be computed just doing an average of the distances that you have among data points belonging to the same clusters. So after you run your clustering algorithm, you just evaluate all the pairwise distances of one point to all the other points belonging to the same cluster, and from averaging these distances you obtain the compactness. Of course, the smaller the compactness, the smaller the distances between these objects belonging to the same cluster are. And this means that we are achieving a better representation or a better grouping of the objects. Because if closer objects belong to the same class, of course, this is something that in principle should be the right way we want that our clustering algorithm should proceed. Instead, the separateness is computed as the minimum distance between two data points, this time one taken from a cluster Ci and the other one from a cluster Cj. So again, you have to compute an average, but this time you take an average from a distance in which one point is kept fixed and belongs to a certain cluster Ci, and the other point belongs to a cluster Cj and varies. You compute all these distances, you do the average, and you take the minimum. And this is the separateness. Of course, since the larger these distances, the larger would be the distance between the point O belonging to cluster Ci and the point O prime belonging to cluster Cj, the better would be the result that we achieved, because the larger the distance between 2 points belonging to different clusters, the more separate the two clusters are, and again this is a desirable feature that we want to address when we select our clustering algorithm. You can easily understand that the silhouette coefficient as defined below as the difference between B and A over the maximum of A and B takes value from -1 to 1 included, and in particular, since we want that the compactness is small and the separateness is high, the closer this index is to 1, the better is the cluster quality. This index is computed for each data object O, and to evaluate the effectively cluster quality, what we have to do is to compute this index for each data object, for each data point in our dataset. And we can display the result of this computation in the silhouette plots, which can be computed with the silhouette function in MATLAB to create these charts, which gives us at a glance the results of our clustering algorithm. As I said, value closer to 1 means better cluster according to the features of compactness and separateness. Values closer to -1 instead means the opposite. So we have clusters that are close to each other, and maybe the points belonging to each clusters are sparse, and this is something that could be a problem when we want to design a clustering algorithm. I'm continuing to say that could be because there are cases in which these two metrics, these two features of separation and compactness are not really descriptive of the data set that we have. But this, of course, is a standard to evaluate cluster quality, and in many real scenarios this effectively works. So if I would have to choose from two silhouette chart based on the same data set running two different clustering algorithms, or the same clustering algorithm but with a different number of clusters as a parameter, which is the one that represents a better cluster quality, I would say that the first one, the one on the left, represents a better result, since the peaks in the negative part have a smaller area with respect to the peaks that you see on the right part. In that case, in this case, we run the silhouette function to evaluate the cluster quality on the same data set, using the first time k-means with two with k equal to 2, so to recognize just two clusters, and the second time we run k-means again but with k equals to 3 to recognize 3 clusters. And you can understand that in this case we would prefer to recognize 2 clusters instead of 3. So you can evaluate cluster quality with the function eval clusters, and you can specify in eval clusters already the algorithms that you want to evaluate or the parameters with which you want to evaluate a specific algorithm. For instance, in this case, running eval clusters using k-means as entry and k-list with the vector 2 up to 5 will result in running k-means many times, every time with a certain number of replicates. For the first group of replicates with k equal to 2, for the second round with k equals to 3, up k equal to 5. For each of the cluster results, this function evaluates the silhouette coefficients, so it evaluates the silhouette coefficient for each data point, and based on that it will return you information, a structure with information regards, for instance, the optimal k found during the different runs. So we have the possibility to address this cluster evaluation with a built-in function of MATLAB, which is eval clusters, and this does not necessarily work with silhouette coefficient. You can specify other evaluation criteria, in which I don't want to discuss here what exactly are, but others are the Kalinski-Habarast criterion, the Davies-Spalding, and also the gap criterion. So all of these are criteria for the evaluation of clustering, and they are very useful when you run class evaluation to understand, for instance, which is the best parameter setting for your clustering algorithm, or if you want to specify different clustering algorithm, which one performs better. So I show you an extra content of the presentation, which is the density-based clustering. If you remember, when I show you the table at the beginning of the cluster analysis techniques, I also mention the possibility to build objectives not based on distances but based on densities. This is very interesting because as we can understand, there may be some patterns in data in which different clusters requires or are described by different distribution, and having different distribution behind that specific cluster may result in a sparser or a denser amount of data for that cluster. So in general, clusters belonging to the same data set does not have the same kind of distribution. There are some clusters that may be more dense, other that may be less dense, and of course with just a partitioning method this is not always easy to recognize, especially if we have overlapping patterns, from which partitioning methods typically belongs to the class of hard clustering techniques, in which the point is or in cluster 1 or in cluster 2, and they typically fail to recognize overlapping clusters. But density-based clustering can help, and in particular the two most famous algorithms that you can find are the dbScan algorithm, which is based on the choice of two parameters, which are a parameter specifying the radius of a neighborhood of a point, also called epsilon, and also another one is the minimum number of points that you want to see in that specific neighborhood, which is sometimes called min points. And based on these two values, based on these two parameters, epsilon and min points, you can assess the connectivity between objects in the dataset and cluster them based on the results of their connectivity. But as you can understand, there are two parameters to tune, and it is not always easy to tune on a dataset two parameters to have a clustering result. So there's another algorithm which works pretty similar to dbScan. In particular, the same metrics regarding the connectivity are evaluated in both algorithms, but optics does not need the choice of parameters. In particular, optics don't even result in a cluster separation, but it resembles more the results of hierarchical clustering methods, building this kind of diagram that you see on the right picture, in which we can relate what is called the reachability distance, which is a parameter descriptive of the connectivity of data points in the dataset, and the order in which our algorithm processes this data. So I know that these concepts may be a little confusing, just described roughly in this way, but if you are really interested, I can do a dedicated seminar on this, or I can also do some short videos to explain better this, and in particular to explain this on MATLAB. I saw now that we reached the 2 hours of streaming. Luckily, I am at the end, so these are the references used to build this presentation. All of them are books. One is a book regarding multidimensional scaling, in which you can find the theoretical part from which I derived some small calculations or some pills on how the algorithm works. I would like to mention that there are many types of multidimensional scaling. Actually, MATLAB, you can, I think, use all of them. All of them are implemented through built-in function. In the MATLAB demo that I have, I just used the classic multidimensional scaling, which is the one which is closer but not exactly equal as the PCA. Again, I recall you that the difference between them is that one works on dissimilarity between data, and the other works with correlation and covariance between data. Then the second reference that you can see is a reference on principal component analysis. Here, the book is very big, but for the one in the chat who asked me curiosities about principal component analysis, you can find all the details here. And also an interesting book on cluster analysis is this one on called Data Mining Concepts and Techniques. It's a very introductory book, so I think you can read this independently on the background that you have. So this was all on my part. I briefly share with you the demos that I prepared. And we can do this in this way, I think. Let's see if I'm changing scene. Yeah, so I now move to MATLAB. I prepared these 3 live scripts. I don't know if I can show you all of them. Maybe I do a brief description of all of them, but I will leave them to you in order to having a look at it, and also to take inspiration if you want to try the things that I explained during the presentation. So I also place the chat here if you have questions, in order to check the chat. If you have any questions, of course, you're free to ask at any time, and I will try to give you an explanation of what you're asking, a good answer. So let's start with eigenfaces. If you remember, this was the first example that I brought to you, and this is called eigenfaces because, by the way, using PCA or singular value decomposition on face images is a computer vision application for face recognition. Of course, nowadays is probably not the best that you can find from the start of deep learning, but still it is. There are many algorithms for face recognition that are based on clustering techniques and PCA, or singular value decomposition, or multidimensional scaling. So this is the website where you can find the pictures that I used. So the live script starts by taking the images that I downloaded by this website. Okay, just to understand, evaluate the number of images that we have taken. Then these images are converted from RGB, so from a color space, to grayscale. and then all the images are reshaped. That means they are flattened to become a 1D array exactly in the same way I showed you in the slides. This is to achieve the X matrix that we want to pass from the PCA algorithm. After reshaping, here is just a picture of some of the photos that I have in the dataset. You can, for instance, understand the distribution of the pixel intensities once you move to the grayscale image with these histograms. And in particular here I used this thing as a debugging tool to normalize images, because normalizing images corresponds to enhancing the contrast of the pixels, and this is very useful for image visualization. So here I run PCA. I also subtracted the mean of the data, but looking carefully at the documentation, I also see that PCA automatically remove the mean of the data. The only thing you need to do is to store this mean, maybe because it is interesting for you if you want to reconstruct the original data set. Reconstruct the original dataset with your principal components. This is a Pareto plot. A Pareto plot can be used to visualize the cumulative explained variance of each of the components. So, as I told you during the presentation, since we have like 40 images and each images has n square number of pixels, but the number of images is smaller than the number of pixels for each image. PCA works on the lowest dimension of the data that we have, that is the dimension along the rows, which means that essentially this problem was a 40 dimensional or 50 dimensional, I don't remember actually the number of images that I took, problem, and this Pareto plot gives you the number of components, which should be equal to the number of images that we have in a data set, and for each of these components, for each of these eigenvectors that we derive with PCA, it gives us the amount of variance explained but that specific component. We can reconstruct our dataset to check if we have done correctly with this equation. Essentially, we add to the mean of our data that is subtracted when you run PCA. We add the matrix multiplication between the scores and the principal components. I recall you that the scores are the projection of the projections of the data in the new subspace that we found with the principal components, and by multiplying them with the values of the principal components, we come back in the original space, since these are the this corresponds to the eigenvalues of the new space, but expressed with the coordinates of the original space. That's why. So essentially, by multiplying by PCS transpose is equivalent to multiply by the Q transpose matrix of my presentation, which is then which end up in the rotating in the converse manner the data set from the reduced data set to the original one. So here is just a way to visualize the reconstructed data set to check if the images are the same. Then we can also check these principal components, which are the eigenvectors of the matrix contained in the matrix PCs. It is interesting because these faces, of course, these eigenfaces, these eigenvectors are affected by, for sure, are affected by the kinds of images that you plug in. So if you had a smaller amount of picture of a woman in the data set, you would probably have this eigenface, how it is called in the literature, with less intense value of light around the hair. So this is to motivate again the answer that I gave it to you before. And again, this will be the result if you just check your, let me see. Okay, these are the things that I plot, y and x. X and y are the two scores, the two columns of the first two columns of the scores, which again reflect the data projected in the new space. So each point here, I overimposed the original image on each point of on the Cartesian plane. Each of these points, each of these image has these two coordinates in the new space represented with basis vector, the first two principal components. So this is a way to deal with dimensionality reduction. There's a brief function to normalize data for the images, and as I told you, this is a script that will be available for you to play. Another example of dimensionality reduction, and here I go faster, is to play with the MNIST dataset. In particular, after having loaded the MNIST dataset that you can download from here, again, I flattened the data, and after flattening the data, I started by playing using PCA, using multidimensional scaling, and also using TSNE, which is, if you remember, another dimensionality reduction technique that I mentioned at one point when I told you that PCA is not able to represent, for instance, nonlinear manifold. It is actually impressive how this algorithm is good in reduce the dimensionality of the MNIST dataset, but I can tell you that this algorithm does not preserve the distance between points, or at least not as well as multidimensional scaling does. So with multidimensional scaling in 3 dimensions or in 2 dimensions, depending on how principal components you decided to keep, you would end up in a more confused representation, but maybe more representative of the real data that you have. Instead, this one is based on also stochastic features present inside the algorithm that I mean, they can give good results, but they require also a particular tuning of the parameters that these algorithms require. I'm going to close this presentation by showing also this live script. This live script regards clustering. this in this live script you see that okay, I downloaded from file exchange a clustering algorithms which is not present in the built-in function, just to play with one more clustering algorithm. I generated synthetically this data, which are generated from 4 different Gaussian distributions, and I start and play with our clustering algorithms that we have. I want to show you a funny thing that is the following. If you use the in this case, since we have synthetic data, we also have the ground truth, which is represented by this plot, and we may decide to use the silhouette function to understand what are the values of the silhouette coefficients in case of correct retrieval, correct assignment of each point of the dataset. And differently from what you may expect, there is a cluster in which the silhouette coefficients are not as good as you want, and this is because this third cluster, which is this one, the light blue one, the Chan one, is essentially overlapped with the fourth cluster, the purple one. This means that there are some points belonging to this cluster which are very close to the points of the purple cluster, and this gives the inversion of sign of this silhouette coefficient, meaning that there are some points in the cluster 3 which they may be compact in the representation of the third cluster, but they are not separate from the cluster 4. And this is the reason why even if you have the ground truth, the silhouette coefficient for the third cluster are not that good as you may expect. Then we run different algorithms, for instance k-means on the same data set, and this is the result as shown in the slide. You have this partitioning method in particular tries to find some decision boundaries here around, and in particular you can see that also this point is misclassified, misgrouped, meaning that probably the decision boundary for this cluster is somewhere between the light blue points and this purple one. Would be a parallel line, probably parallel to the to the axis of this ellipse. Of course, you can see that since this is a hard clustering method with superimposed clusters, it's very difficult to deal with. An alternative could be to use fuzzy c-means, which is a soft clustering version of k-means. This is also present in the built-in function of MATLAB, but does not belong to this basic toolbox of machine learning. You should download another toolbox to have it. Paradoxically, if you use k-means to cluster this data, you would find a silhouette chart that is even better than the one you had obtained here. This is to say, silhouette coefficient is good to evaluate cluster quality, but is not always good enough to describe clusters, especially if they are overlapped. Puoi fare un po' di roast. Potrei provare a farlo in un prossimo seminario, sì. Ti ringrazio. Let's keep going using Gaussian mixture models, again called with the same function that I showed you in the presentation to cluster this data set. And as you can expect, This is probably the best way to cluster this dataset, just because all of the clusters are Gaussian distributions. So since Gaussian mixtures use Gaussian distribution to fit the data, he will probably be able to cluster these in the correct way. Then other things that I tried is by using a hierarchical clustering algorithm. In particular, I tried different linkage metrics, and the ones that I found to be the best is the word method, which together as the complete method are the ones that tends to group cluster based on local features instead of global features, and these are the only linkage that really helps you to solve this problem. If you try with a single linkage, you would end up in a complete green screen, everything recognizing the same cluster except 2 or 3 points that are far from the others, which are on its own recognized as cluster on their own. So using single linkage will result in having a big cluster and 3 other small clusters represented by 3 single points. You can try if you want by modifying this script, changing here word with single linkage. And then there's this extra content of using the software that the implemented clustering algorithm that I downloaded from File Exchange, which is called Optics. It is one of the 2 clustering algorithms that I showed you during the presentation as an extra content. This is not present in MATLAB. dbScan instead is present, but again, dbScan is not present in the machine learning toolbox, so you need to download one more toolbox to use it. And spoiler, this is the result using a density-based approach using optics. It is pretty impressive. It is not as good as using Gaussian mixtures, but I mean, if I perturbate a bit this distribution, adding other random points somewhere, probably this algorithm would outperform in terms of results the use of Gaussian mixtures. But in this case, as expected, this approach performed well. As you can see, it can be used also for doing soft clustering. So a density-based approach can be used in soft case scenario, although it is not a soft based, since each point almost belongs to just one cluster, and this is the chart from which you can derive the structure. As you can see here, there are 4 steps, and each of these steps represent these 4 clusters essentially. This is another challenging scenario in which I took another synthetic dataset, and here I tried again other algorithms. Actually, I tried the same algorithms, but for dealing with this dataset, but using also cluster evaluation to find the best parameters for that clustering algorithms. But I leave this for you to check if you're curious when playing with this live scripts. So this was all by my side. Thank you, Augusto. I hope you enjoyed this streaming. And if you are interested in other videos on this, please follow the Facebook group of MATLAB UniP, and also if you want the other Facebook group of the other university, join our YouTube channel, and soon we will also give you the link to stay updated in all the events because we have built our own website. I'm really happy of the outcome of this seminar. I hope you're happy too. And again, if there are no questions, I will conclude the seminar here. Okay, so instead of the show must go on, the show must finish. So I thank you all again, and thanks everybody for watching. We will see in the next video, and hopefully in a live event instead of just an online event. Thank you.